Hi there! Welcome to a new physics lesson filled with adventure and discovery. Today, our lesson is on simple harmonic motion. And so we're going to go over how we what is that? What is simple harmonic motion or periodic motion? And second of all, how do we use that to look at transfer of energy? How do we use that to describe, what are some examples of that? That's what we're going to go over today. So let's jump into it. So what is simple harmonic motion? When we look at our universe and we look at our world and the earth that we live in, we notice that there are some things that have what we call periodic motion. And well, what is that? Well, periodic motion is whenever you have something that every so often it repeats itself. It's periodic. Every so often there's a pattern. And simple harmonic motion is one example of periodic motion. And it's the most simple, obviously, simple harmonic motion. So we can describe it as a vibration around the equilibrium point, in which there's always a restoring force that brings it back to what we call equilibrium. Okay, and that restoring force is always proportional to the displacement from equilibrium. So if we displace it from the equilibrium, there's a restoring force that's always going to bring it back to equilibrium. Or in more simple terms, simple harmonic motion is whenever we have back and forth motion. And so you might think, well, what are some examples of that? Well, if I have something hanging from a string and it's just rotating or it's vibrating around the equilibrium point, eventually it's going to come to a stop. But if I move it a little bit from the equilibrium point, if I displace it, it's going to move back and forth. That's an example of simple harmonic motion. Okay, so let's look at some examples of that and how we can quantify simple harmonic motion. First of all, one of the most simple examples is whenever we have some kind of mass attached to a spring, and we can either compress it or we can stretch it. And however, if we let it go, after a while it's going to reach this equilibrium point, which is this middle section A here. And so here's some questions to kind of ask when we're talking about simple harmonic motion. Where is the block's maximum, minimum displacement, velocity, and acceleration going to be when we have this simple harmonic motion? Okay, so we're going to be taking a look at that. But you can kind of figure it out already. First of all, displacement. Where is the maximum displacement? Where's the maximum delta x? Well, if you stretch the mass here, or you compress it here, that is going to be its maximum. Okay, or maximum displacement. Where is its minimum? Well, we're going to say that the minimum, since its resting point or its relaxed state is the equilibrium point, when the spring comes back to equilibrium, that's its minimum displacement. Okay, its velocity. If I stretch the string out or the spring and I let it go, where is this maximum velocity going to be? Well, it's going to speed up, speed up, speed up, speed up, and then as it reaches this point here, I'm just going to slow down. And so we can say that the maximum velocity will probably be in the middle here, A. Minimum being the outsides when it compresses or when it stretches. And an acceleration, the greatest acceleration is actually going to occur, when is it going to speed up the most or slow down the most? Well, again, it's going to be whenever we stretch it or we compress it. That moment that we let it go is going to be its maximum acceleration. Okay. And so we can summarize it. Where is the maximum displacement? At the ends of our spring, mass on a spring. Minimum is going to be at equilibrium point. However, velocity is the opposite of that. Velocity maximum, the greatest velocity of our mass on a spring is at the equilibrium point when it's right in the middle. Minimum being when it reaches the ends, when it's compressed or when it's stretched. And last of all, acceleration follows displacement. It's going to be greatest or maximum at the ends when we compress it or when we stretch it, and then it's going to be the minimum. It's going to reach about constant velocities somewhere in the middle at the equilibrium point. Okay, but how can we quantify simple harmonic motion? Well, there's this thing called Hooke's law, and notice it's kind of in the same format as Newton's law. It's kind of like a F equals ma equation. But notice instead we have force is equal to the negative spring constant. K is a spring constant in newtons per meter. And it will be multiplied by the displacement. And so the spring constant and the displacement are going to be have a negative relationship with each other. It's negative because whenever you stretch that spring and let it go, it's going to start moving, or it's going to be force. That restoring force is going to be pulling in the opposite direction that you displaced it. Whether it's scrunching, if you scrunch the spring or you stretch the spring, it's going to move opposite of however you squished it or you stretched it. That's why it's a negative. So what does this look like on your quiz? Well, here's an example, and notice I have a little picture down here for you. So let's say we have a mass on a spring, and that mass is 0.55 kilograms, 0.55 kilograms, attached to a vertical string that stretches a spring 2 centimeters from its original equilibrium position. What is the spring constant? So the beauty of this is we're able to figure out the spring constant using Hooke's law and also the force due to gravity. So what are some things we know? Well, first of all, like we just covered, we know Hooke's law. We also know that all the net forces have to equal up to 0. And so what are the forces acting upon this situation here? There's two of them. One of them is gravity, so Fg, which is how do we calculate the force due to gravity? Mass times the gravity. And then lastly, we have this elastic kind of force, this restoring force due to the spring, which is going to be our negative kx. But both of those two things added together, the force due to gravity, which is negative because it's going downward, is pulling downwards, and the force due to this elastic spring is positive. Okay, that's going to have to equal to 0. So for to substitute to actually calculate for this, we get a negative mg is equal to negative kx. It's negative because it's downwards. That gravity acceleration due to gravity is negative 9.81. So I'm just going to move it to the front. And then if I add this to the right side here, we could get a calculation to solve for k. So what I'm going to do is I'm going to add this to the right side of the equation so I can calculate for k. The spring constant. And so once I do that, I get this equation. I plug in all my numbers. Notice I have 0.55 kilograms as the mass, negative 9.81, the negative's up there. I just took it out of here. You could just leave it as negative 9.81. And that's going to be equal to k, which is positive because I added it to the side, k times, and notice I stretched it downwards here, so negative 0.02 meters. So you calculate for that. K should be equal to 270 newtons per meter. That is the spring constant for this problem. Okay, we're moving on along. So conservation of simple harmonic motion, because there's this restoring force that either moves a swinging object or the mass on a spring. Once we cause a displacement from the equilibrium point and let it go, we add energy to that situation, and that energy can be transferred back and forth. When we stretch the spring, the mass on a spring, and then let it go, initially it has elastic potential energy because of that spring. It's stretched, and so when I let it go, it's going to start moving, and that spring potential energy is going to turn into kinetic energy until it reaches that scrunch state. Once it reaches that scrunch state, it's going to convert all of its kinetic energy back into potential energy. So notice here the maximum kinetic energy and the least potential energy is that middle point where that mass reaches that equilibrium point. But throughout this equation, throughout the situation, the total mechanical energy is conserved. There's no loss of energy, conservation of energy. Okay. So yeah, notice here maximum displacement in the other direction, and B is the equilibrium point. So what we can say then is that spring energy can be converted into mechanical energy, or in other words, energy in motion, so that's kinetic energy. And so elastic potential energy from whether it's a mass on a spring or even a swinging motion pendulum we're going to talk about in a moment, that can be converted into kinetic energy. So one good example of this is a bow and arrow. If I stretch it, if I displace that string, I'm going to stretch it, there's some elastic potential energy there. And so if I let go of that string, it's going to convert that into kinetic energy, which we can use to shoot the bow and arrow. And so here's an example of that. Let's say we have a bow and arrow that shoots a bow that shoots an arrow velocity of 25 meters per second, and the arrow has a mass of 0.25 kilograms. If the bow has a spring constant of that, what is the displacement that I drew back the arrow? What is that displacement there? And so a couple things we know. We know that initially when we drew back the arrow, that's elastic potential energy, and once we let it go, it turned into kinetic energy. That arrow moved. And so we can use this equation, right? We can replace the EPE with 1/2 kx squared, and then the KE with 1/2 mv squared. And notice we have all these variables, so we can plug them in. 1/2 K in this case is a spring constant, newtons per meter, 260.4 newtons per meter. We don't know the displacement of the arrow or how far back we had to draw it. Is equal to 1/2 the mass of the arrow, which is 0.25 kilograms, and then the final velocity of that arrow, or the velocity of the arrow, which is 25 meters per second. And so if we make the calculation, solve for x, and don't forget to take the square root, you should have got 1.1 meters. So I'm drawing back the arrow about 1.1 meters, okay, in order to attain that kinetic energy, that velocity. And like I mentioned earlier, the other really good example of simple harmonic motion are pendulums. And pendulums are always really cool to play with. You see them swinging back and forth. And so a pendulum is whenever you have a hanging mass not from a spring, but from a string. And so whenever we have a pendulum at a small angle, so less than 15 degrees from the equilibrium point, we get this pendulum motion, which in this case, the restoring motion is not a spring anymore, but rather it's gravity pulling it back to this equilibrium position. Okay, and so again, it helps us to describe this pendulum motion by looking at three variables: its displacement, velocity, and acceleration, as well as its potential energy and kinetic energy. And so if you were to take a guess, what is the maximum minimum displacement of this pendulum from the equilibrium point? What is the maximum minimum velocity? Where is it reaching its maximum velocity or speed? Is it A and E, or is it C? Same thing with acceleration. What is the maximum minimum? And then lastly, potential energy and kinetic energy. Where does it have the most potential, least potential, most kinetic energy, least kinetic energy? Why don't you take a guess before we flip to the next slide? And hopefully you'll see that there's a lot of parallels between this and the mass on the spring. Okay, so hopefully you took a guess and maybe you jotted it down, or maybe just in your head. For displacement, the greatest displacement from the equilibrium point, C is the equilibrium point, would be A and E. Okay, it's greatest displacement. Its minimum, of course, the equilibrium point C. Max velocity of this ball on a string from this pendulum. Well, just like the mass on a spring, it doesn't have any velocity when it's on the ends. It's going to have, at the equilibrium point, it's going to have its maximum velocity, so C. And then minimum, like I said, are the ends. So A and E, it wouldn't be moving at all. Acceleration, however, it has the greatest acceleration. It's going to speed up the most when it reaches A and E, these ends. The least acceleration when it reaches kind of a constant velocity, so no acceleration, would be C. Its greatest potential energy, its greatest height away from the equilibrium point would be A and E, least being the equilibrium point. And then last of all, our kinetic energy directly follows its velocity, so its greatest kinetic energy is C, minimum A and E. Okay. And so here's just kind of a summary of both of these, kind of comparing the two. And notice it's very much the same. When do you have maximum displacement? When it's either stretched out or when it's pulled farthest from the equilibrium point. However, it will reach equilibrium when it's in the middle here, or middle of the spring. Okay, and then okay, so it's just showing you as it swings back and forth, kind of what our values are for force, acceleration, and displacement velocity. Okay, and so hopefully you're starting to get this concept of periodic motion. Today we're just introducing it to you through simple harmonic motion. And so thank you so much for joining us, and we'll see you next time.